Okay, this is the fifth video in the algebra section. This is on simple transformation of graphs. Slight misnomer, these can be quite tricky and confusing, but that's just the way it's known in the various syllabuses. What are we talking about? Well, this is an example which helps us to talk about it. A curve has equation y equals f of x. I've just used y equals x squared here, a simple example. In fact, this whole video, really, I'm just using simple algebraic functions to illustrate the point. There'll be further videos which look at more complicated functions, but the function could be anything. It could be a trig function, sine x, or some more complicated thing involving algebraics, trig, exponentials and logs and so on. But yeah, so here just illustrating with simple examples. So the first transformation, basically we're just adding 2 on to the function. Yeah, so every y value that we've calculated on here is going to be uplifted by 2. So we're going to get this case here. So this is that first transformation. Now the second one is y equals f of x minus 2. So to actually graph this, what we need to do is we need to replace every occurrence of x in our function, and we've only got one here, by x minus 2. And that has the effect of shifting our original curve to the right by 2. Now, just to emphasize, we've got to replace every occurrence of x in order to get this transformation. So if we've got this function, e to the power of x minus sine x, then we would need to do this substitution in order to affect that shift right by 1. And that will be a 1. We're talking about a shift by 2 here. Okay, but we need to replace every occurrence of x by what's in the brackets, basically. The third one, y equals 3f of x. So what we're doing here is for every every y value we've calculated, we're multiplying it by 3. So it's basically gonna stretch the whole thing upwards. Look here, if we got a value of 2 here, then that's 4 on the y-axis. So 2 here is going to correspond to 12 up the y-axis. So it's a stretch up by 3. And the final one is f of 2x in this case. And what we're doing here, we're actually squashing it in. It seems slightly counterintuitive, doesn't it? F of 2x. So here we're replacing all x's by 2x, our function. And this squashes it in this case, in towards the y-axis. It seems slightly counterintuitive, but if you imagine an even simpler case, the graph of y equals x, for instance, if we were to replace all x's in that by 2x, then we've transformed from something with a slope of 45 degrees to something which is steeper, essentially squashing it in. So might be just an image to keep in your mind, which might help you remember that. Okay, let's have a look. We've also, when we're doing our stretching or squashing, if the factor by which we're stretching or squashing is negative, then not only are we actually stretching and squashing it, but we're also reflecting it. And of course, if that stretch is of absolute value 1, then we're just doing a reflection. So here we've got a slightly different curve, x squared minus x. So if we were to replace every x in that function by minus x, then this is what we've got. This can obviously be simplified, but I've just shown it in this sort of this raw form. So we're actually transforming from this red curve to the green. So you can see that is a reflection in the y-axis. And then if we are to if we're doing want to do a reflection vertically, i.e. in the x-axis, then this is going to perform that. So this is a little bit similar to our y equals 3 times f of x on the previous page, except our 3 is a -1. So we're transforming it in the vertical direction, but in this case, we're doing a reflection. Okay, so those are the key types of transformations. It starts to get interesting when we combine these together, though. That's the thing. So let's have a look at some other examples. And what we're going to do, first of all, is just look at horizontal transformations, where perhaps it's kind of the most confusing and obscure. Lift that up there. Let's have a look at this form. Going back to x squared as our example here, y equals x squared. And this is similar to what we've just done. We replaced all our x's by x -1. We've got a shift of 1 to the right. This is another similar one. X squared is we're replacing all our x's by 2x, so we're getting that squash in again. Okay, so we squashed it in, taking apart the space effectively. Now what we're doing here, we're combining two together. So what we've done is we've shifted it right by 1, and then we've squashed it in by this factor of 2. Okay, so so we can see that I put the yellow vertical line there, because that demonstrates that actually we've shifted it, but then when we're squashing it in, we're squashing it into this line here, which is x equals 1. Okay, so let's keep that in mind. Well, I've got something similar here. So you might be tempted to think, well, yeah, what we've done is we've squashed it in and then shifted it. Okay, squashed it in and then multiplied by 2 and then shifted it. But actually, if we look at this graph here, here's our original x squared. This is definitely squashed in, isn't it? But what's it squashed in towards? Well, it's squashed into x equals a half, which doesn't really represent a shift to the right by 1 at all, does it? So, and I think you probably see that we could write this as 2 into x minus a half all squared, in which case, comparing it to this, it's quite understandable that we're only actually shifting it by a half. Okay, so it's horizontal transformations. Yeah, let's just have another look at this then. Why is this? I think without overthinking this a little bit too much, it might just be worth just seeing it in a slightly different context. So here we've got that same thing, x squared, and then this 2x minus 1 all squared. So I think the thing that we might just bear in mind is that these are our x values along the horizontal. What we're sort of doing is we're actually doing a substitution. Substitutions are useful right throughout calculus, but actually quite useful here as well. So if we think about u equals 2x, that's what we're doing. We're doing a squash with this. Well, essentially, what we therefore do is we're at all these are the u values that correspond to the x values. Okay. So in a sense, we're you can think that we're transforming the curve, but we're in another sense, what we're doing is we're actually changing the axes, whether either scaling them or shifting the axes. So it's kind of another way of of thinking about it. If we then go on to say, right, well, now we do a second substitution, we represent our shift, v equals u minus 1, then what we're actually doing is, well, these are the v values, and you can see, I mean, they are actually acting on these u values. So, if we shift to the right 1, v equals u minus 1 to the right 1, then our 0 in v terms comes to here, which is where this curve bottoms out. So here we go. So a word of caution on there. We'll come to this again in a moment. But we have to be careful how we write our horizontal transformations. Okay, so let's have a look at the more sort of general case. We're looking at sort of composite transformations. If we do a number of different things, let's have a look at the horizontal in the first place. So what we've got is this is the general case. So we're not thinking about shifting it up. We're just thinking about horizontal shifts here. So yeah, a function of well, here I've got the shift and the stretch squash all in the brackets here. So we could have both of these, or we could have a b of 0, or we could have an a of 1, a b of 0, or an a of 1, which basically would just leave us with a horizontal translation. So an a between -1 and 1 means stretch out. So a half would actually make it wider. A of less than 0 is a reflection. We've said that. And b of greater than 0 means this is going to be shifted right. And if it's negative, we're going to have something like x plus 1 then, and that would be a shift left. So b is the total shift, a is the total stretch, and so that's what that's describing, sort of no matter in which order they are done. As long as you write it like this, then basically we can compound all these things together. Let me just give you an example. So if we start off with y equals x squared, and we shift it right by 3, we're going to end up with this. If we then stretch it by 2, we're going to get this. So this is kind of, looks like that, doesn't it? If then we shift it left by 1, then what we're doing is we are our sort of central axis or reference line vertically for this curve is going to be x minus 2. And then if we squash that, then squash it by a third, that means we're going to multiply it by 3. Our a is going to be 3. So we're going to multiply this by this half by 3. So we're going to end up with this. Okay, so this, now when we look at this, this really is just 2 transformations, isn't it? This is a right shift by 2 and a stretch squash by 3 over 2, which would be, overall would be a squashing in. Okay, so that's how that works in the horizontal direction. So we can compound these things together, but we really want to keep it in this form. Now, very often when you're looking at problems like this, it won't be expressed like this. It will be expressed in the form, 2x minus 1, for instance. So you would need to unpick that and write it as 2 into x minus a half in order to understand exactly what that transformation was doing. Now, in the vertical direction, the behavior is actually slightly different, which is a little bit confusing. But if we've got our transformed function here, transformed horizontally, then basically we can we can squash it up down by multiplying it by c. That was one of the first examples, wasn't it? And then we can translate it by d. And if d is positive, then it's a shift up. So again, c between -1 and 1 means a squash in this case. C less than 0 is a reflection, and d greater than 0 is a shift up. Okay. Now we could do the shift up and then and then do the stretch. So it would look a little bit more like this potentially. But you really have to look at the actual function and just kind of decompose it in a way that makes sense. Shifts and stretches are always done from the x-axis and applied in the order that they are done. So we're going to multiply by C, then add D, then we might multiply by another C. So that would be multiplying the whole lot. And then adding another D, which would go on the end, and so on. So we need to we kind of build it up, and those are always those shifts and stretches are done from the x-axis. So here's an example. So y equals x squared plus 3. That's so if we take our original curve of y equals x squared, we're shifting up by 3. If we stretch it by 2, we're going to have this thing here. And now if we move it down by 5, so if we're moving this down by 5, we're going to take this and then subtract 5 from it. And then if we then stretch it by 3, we're going to multiply this whole thing by 3. Okay. Now, if we want to rewrite that, we rewrite that as that. It doesn't really give a lot of clue, does it, about what's been going on? But that's what we would end up with. So the sum total of those 4 things would be this curve here. Okay, so we've kind of looked at horizontal and vertical, and say you have to kind of think of them in slightly different ways if we are compounding or producing composite transformations where we're doing a number of different shifts and stretches and so on. Okay, so that is that. Let's have a look at an example. So we're going to go back to our example of x squared plus x. All right, so we're just going to do 4 things. We're going to do all 4 things, or all 4 of those options we started with on this particular curve. So first of all, we're going to shift right by 1. So every occurrence of x has been replaced by x minus 1. So that's given us that. So that's what this translation is here. Shifted it from the green to the red. We're going to squash in by 1/2. So that's so for every occurrence, we're going to replace, well, now x minus 1 by 2 into x minus 1. So we've done that there and there. And that's what that does. And so just to say, if this is the curve that we're dealing with here, that's the red curve that came out of the previous step. We are squashing it in towards this yellow line. So I think perhaps you can see that. Just go along there. Where the blue crosses this axis here, it's half the distance of there. Similarly, this point here is half, or that distance, I should say, is half of that distance, and so on. So yeah, it's all been squashed in, and you can say the same thing about the right-hand side as well, is this distance is half of this distance. So then we're going to shift up by 2. Right, we've just added 2 onto what we've got. So that blue curve that's come out of the last stage, we've shifted it up by 2 to get this green curve here. Okay, that's fairly straightforward. And then we're stretched up, we're stretching up by 3. So we're just multiplying it all by 3. And everything is 3 times as far from the x-axis as a result of that process. Okay, so that illustrates something where we're doing a kind of multiple stages. So does it matter which order we do these in? Well, yeah, it does. I mean, within the horizontal, then we could do those in either order, because we're going to end up with this. in the case of the y direction, then it does matter which order it is. So we would get a different result if we did 4 before 3. Okay, so I hope that's clear from what we've said before. Right, let's have a look at 1 or 2 examples. Diagram below shows the graph of y equals f of x. We don't know what that function is. We don't need to know what that function is. Looks like a negative cubic coming down from top left to, and then finishing up going down to the right, but we don't know. The marked point 4, 8 lies on the graph, and the graph meets the origin at the marked point 8. In separate diagrams, sketch the curves, first of all, with this equation, y equals f of 1/3 of x. Well, this is going to be a stretch out in the horizontal direction, stretch by 3. So whilst this point, because it's on the y-axis, it will stay where it is. But everything else, including this point here, will be stretched out by a factor of 3. So if this is stretched to the right by a factor of 3, then it's going to be B12, 8. So it asks us to give the coordinates of the images of the points A and B under the given transformation. Well, yeah, A would be the same and B would be this point 12, 8. And then secondly, 6y equals f of x. Well, in this case, we imagine the 6 on this side, it'd be 1/6 f of x. So it basically will be a squashing down by a 1/6. Again, the point A is going to staying put, but this point's going to come down to here. So the 8 is going to become 8/6. So that would be the answer to that part. Okay, right, let's go and have a look at another example. Right, this is a slightly different thing. Given that f of x plus 3 equals this cubic expression here, find f of x. Okay, so what we need to do is we kind of need to work it backwards here. And we can do that by, if we subtract 3 from this, then basically what you can see we're going to end up with this. This is just f of x, isn't it? But what we're doing by doing that shift is we're going to actually subtract 3 from every occurrence of x in this cubic here. So x minus 3 cubed plus 9 to x minus 3 squared, and so on. And if we work this through, expand and simplify, we're just going to end up with x cubed minus 1. So that is f of x, and we see this. If we rewrite this, we can just take the brackets away, and we're left with f of x. If we could check that, by the way, by then transforming it back to the right. So if we actually then transformed it by to the left, plus 3 to the left, then we would have this. And indeed, if we expand this, we get that, which is our original curve. Okay, so I think that's quite an interesting little example. Now, this one is quite a tough little thing. But if we go through the steps, it's not too bad. The graph of function f of x equals ax squared plus bx plus c is transformed by this sequence. A reflection through x equals 0. Okay, so x equals 0 is horizontal axis. A translation by a vector. So this is basically, it means shifting to the left by 1 and shifting upwards by 3, and then a horizontal stretch with scale factor 2, stretching it out by 2. And the resultant function is this 4x squared plus ax minus 6. Find the values of a, b, and c. Okay, right. Well, what we've got to do here is we've actually got to do these 4 things on this curve. Now, we haven't got the numbers, have we? But you know, we'll get to that. So after the first stage, what we've done is we have just multiplied the whole thing by -1. That is what that reflection is, giving us that. Secondly, we're doing a translation left. We're going left by 1. Well, that means that we replace our x's by x plus 1. It's there and there. Okay, stage 3 is a translation by 3 in the y direction. So we're just going to add 3 onto the end there. And then a horizontal stretch with scale factor 2. Right, okay, so our x plus 1s are going to be multiplied by 1/2 here. Okay, so remember, in the horizontal direction, something less than 1 is going to stretch it out. Right, so that is that. Well, what we've got to do now is we've just basically got to multiply this out. We're going to get this. And we're comparing this expression now with this 4x squared plus ax minus 6. Okay, so it's a bit messy. I'm not going to go through it in detail, but we've just got the one term there for the x squared. That's going to be 8 minus a over 4 is equal to 4, so a equals minus 16. We look at the coefficients of x, and we get this equation here, just like that. But we know what a is. It gives us b equals minus 3a. We know what a is, minus 16. So b is therefore 48. And then we kind of got all the bits. So we can work out what c is, and that comes to minus 11. So that's the answer we're looking for. A equals minus 16, b equals 48, c equals minus 11. And therefore the transformation is minus 16x squared plus 4x minus 11 goes to 4x squared minus 16x minus 6. And it's a result of knowing what a is. So that is quite one of the more difficult ones, I'd say, in terms of these sort of questions. Basically, that's, I think, as much as we need to do in this video. There will be other videos on transformations, which are looking at composite transformations where we're doing a number of different shifts and what we end up with, trying to possibly work back from functions to work out what operations have been done, and certainly looking at problems involving trig functions, log and x functions, which provide a little bit more interest and complexity. But hopefully you found that useful and interesting. And thank you for watching.